So this is what we did in the last video. So how much is the delay of this circuit? Well, the same as the delay of a 2 to 1 mux, yeah, which is the delay of two input gates. Yeah. So let's just say that the delay is constant. It does not grow. It's not a growing function of n, which is the length of x. It's a constant delay circuit. Yeah. Okay. Now this was for shifting by 3 positions, but you can do the same thing and implement shifting by any other fixed number of positions. Now we'd like to build upon this idea and extend this design to support shifting by a variable number of positions, which is specified as an input t. So t again, once again, let's remind ourselves that t is an integer between 0 and n and specified, so written down in binary. Yeah. So how many bits will you need to write down t? Well, log n plus 1 to the base t, ceiling of that. Okay, so yeah. So again, for the sake of concreteness, let's say n is equal to 6 and t is an integer between 0 and 6. So again, x1, x2, x3, x4, x5, x6, this is x, and now we have t, which is a number between 0 and 6, so we'll need 3 bits to write down such a number. So t is a 3-bit string, let's call it t0, t1, t2, and t0, t1, t2. So our circuit, it's called this t. So our circuit has these 9 inputs, yes, and y is y1, y2, y3, y4, y5, y6. So like last time, we will design a circuit for each YL and then put them all together, and that's going to be our final circuit. Yes? Okay. So let's begin with Y1. What should Y1 be? Now that depends on t. So if t is 0, Y1 is equal to x1. And if t is greater than 0, then Y1 is 0 basically. Yes? So again, we can design it by a multiplexer, but it's a 3 to 8 multiplexer, because it has, so these T0, T1, T2 are going to be the select bits in my multiplexer, and it will have 8 output lines. We won't need all of them. We'll need only 7 of them, because T has 7 possibilities really. So 0 to 6. Okay, so Y1 should be x1 if T is all zeros. Yeah. So the first data line should be connected to x1, and the output line of this mux will be y1. And now if T is something between 1 and 6, then y1 should be 0. Yeah. So I will have 6 zeros here. Yeah. Let me draw it slightly bigger. It also has another data line, and it's not important what we connect there. Yeah. So let me put a phi here to indicate that that is irrelevant. We are assuming that t will always be a number between 0 and 6, and t will never be equal to 7. So t0, t1, t2 will never be equal to all ones. So y1 is equal to x1 if t is 0, 0 if t is 1, 0 if t is 2, 0 if t is 3, and so on. And this is the circuit for y1. Huh? Okay. y2. So if t is 0, then y2 is equal to x2, no shift. If t is 1, then y2 is equal to x1, shift by 1 position. And if t is between 2 and 6, then y2 is 0. So I will put 5 zeros here. T equal to 2, 3, 4, 5, 6, and the 8th data input again will not be relevant because t will never be equal to 7. Yeah, sure. So we will have one such marks for each yi. So let me leave the marks for y3 for you to design, and let's see the marks for y4 maybe. And then leave the remaining marks for you to design. Yeah. So if t is 0, then no shift, y4 is equal to x4. If t is equal to 1, y4 is equal to x3. If t is equal to 0, y4 is equal to x2. If t is equal to 1, y4 is equal to x1. I'm sorry, if t is equal to 4, y4 is equal to x1. And if t is 5 or 6, sorry, I think I made a mistake. So if t is 0, then y4 is equal to x4. If t is 1, y4 is x3. If t is 2, y4 is x2. If t is 3, y4 is x1. And if t is 4, 5 or 6, then y4 is 0. So this corresponds to t being 4, this corresponds to t being 5, and this corresponds to t being 6. And the 8th line again is irrelevant because t is never equal to 7. Yeah. Okay. And thus, if you put all these mux together, we will have some circuit for the barrel shifter. Yeah. So, and so in general, this is for n equal to 6. In general, each mux will be so let us say n plus 1. For simplicity, let's assume that n plus 1 is a power of 2. So n plus 1 is, let's say, 2 power k. Then you will use a k cross 2 power k mux, yes, for each output position. So the number of gates in such a mux will be, well, so the asymptotics will be like order of 2 power k, that is order of n. So the complexity of the circuit grows linearly in the length of x, and that is for each output bit, each yi, and there are n of them. So in total, the size of the circuit is order of n square. However, it's a fast circuit. The delay is, yeah. So a multiplexer generates all the minterms of the select bits and then ANDs those minterms with the corresponding data lines. Yeah. So if those minterms are generated by single multi-input AND gates, then it's a constant delay circuit. Otherwise, its delay will be slightly more, but still extremely nominal. Okay, so however, the number of gates in this circuit grows quadratically with the length of x. So we'd like to explore possibilities of coming up with a cheaper design, and in digital design it's always about trade-offs. So we'll see that we can bring down the size of the circuit, but we'll have to pay in terms of the delay or the computation time. Yeah. And in the next video we'll see what kind of deal we can strike.